2, 1.
Srijith, you're supposed to defend our position.
Little cave, and I have the heart to say no.
3, 2, 1, go.
Degrees.
3, 2, 1. Four, 5, 3,
45 degrees.
1.
This is 45 degrees.
Approximately. It's actually 50 degrees outside.
Stop.
Which of the three characteristics above, when varied, had the greatest effect on the period of swinging?
Okay, so when we did our experiment, the 3 characteristics we tested were the mass of the swingers, the swing length, and the angle from which we released the swing from. And out of these, the length had the greatest effect. And we know this because the equation for the period of a pendulum is only affected by gravity and the length of a swing. And since gravity is constant, only the length matters. So the period of a pendulum is proportional to the square root of length over gravity. Mass isn't even part of the formula, and the angle of release is not part of the formula either. So the answer is length.
Good job. To verify that changing of the mass has no effect on the period of swinging, have the lightest and heaviest members of your group swing side by side, and the question is it relatively easy for the two swingers to synchronize, and why?
It is pretty easy. So the lightest members of our group are me and Hugh. And it is easy because we have the same period, and we have the same period because the swing lengths are the same. We just explained this, but the period is proportional to the square root of length over gravity, and gravity always is the same, and mass is not in the equation at all. So the only characteristic that matters is swing length. But the hardest part about synchronizing is that it can be difficult to start at the same height and at the exact same time, but our synchronization should be the same because our swing lengths are the same.
Trial 1.
Alright, stand.
Trial 2.
Yeah, I'm gonna start the timer. Keep spinning. Once you reach it, I'm starting the timer, yeah. Alright, release. Keep spinning and walk forward.
Is he gonna have to be going faster?
Alright, ready? Okay. That's fine. That's first trial done.
Did it?
Oh, release.
This is trial 2.
No. Right. Go to C. Now move forward. Yeah, move forward.
Go.
That's fine. Just move forward and then rotate. Move forward and rotate.
Alright, ready, go.
Release.
Counting.
Start spinning.
Srijith, I think it'll help you if you fall off if you lean forward, like a little bit.
Let go. Okay.
I'm going 3 times.
Watch out, man.
Alright, release.
Go in the hole. Yes.
Okay.
The merry-go-round. What would happen if your feet slipped while you're spinning around? Would you fly off away from the center merry-go-round? Would you continue in a straight line, or would you fall towards the center?
We tested this on the playground by having one person spin on the merry-go-round, and they dropped a tennis ball after they passed the person who was on the ground observing. And so we figured out that you would continue in a straight line because the linear velocity travels in a line tangential to the circumference of the circle. And in addition, when we fall, there's no more friction, which means there's no force that gives us centripetal acceleration. So we no longer accelerate towards the center, and we would continue in the same direction just before we slipped.
Okay, next. Describe below the path the ball took when released from the viewpoint of the rider and the observer.
From the viewpoint of the observer, the ball flew in a straight line tangential to the circumference of the circle, but from the perspective of the rider, it seemed to wrap around them because while the ball was going straight, the rider was still traveling in a circle on the merry-go-round.
Good. From the perspective of the spinning merry-go-round, what are the forces on the ball as the merry-go-round turns? And what are the forces from the perspective of the observer on the ground? What are the forces on the ball? And after the ball is dropped, which observer's forces are useful in describing the ball's motion?
So the forces on the ball are always going to be the same. The only difference is that the person on the merry-go-round and the person on the ground, the relative direction of the ball to them is different from their perspective. But the forces on the ball are gravity, air resistance, the normal force, and tension from the arm. The arm acts as the tether and holds the ball, which keeps it rotating in circles. But when the ball is released, only gravity and air resistance are acting on the ball, so it falls. But there's also initial velocity, so it continues flying in a straight line while accelerating down. So after the ball is dropped, the forces that the ground observer sees are more accurate in describing the ball's motion, because if you're the person on the merry-go-round, the ball's direction to you is always changing. The relative direction to you is always changing because you're still spinning around. So after it drops, the person on the ground would describe the motion more accurately.
What happened to the period of revolution when the person walked towards the center of a merry-go-round?
So the results of our experiment were the opposite to what was expected. Our period got longer, and we attribute this to the force of friction acting on the merry-go-round, causing noticeable deceleration right after I let go. What should have happened was the period should have gotten shorter because inertia should have become smaller.
In this experiment, the radius decreased as the person walked towards the center. Did the speed decrease, stay the same, or increase? And how did you know?
The speed decreased because the period became longer. However, the speed should have increased because, if there was no friction acting on the merry-go-round.
And lastly, what must happen to the person's speed then, if angular momentum is being conserved? And did you observe this?
If angular momentum was to be conserved, the person's speed would increase. Angular momentum is equal to the product of mass, velocity, and radius. And if radius is decreased and mass and angular momentum are held constant, the velocity would also increase. This was not observed because the velocity of the person on the merry-go-round was decreasing rapidly due to the friction from the axle on the merry-go-round.
So this is just a disclaimer. We got the opposite results of what should have been expected for the merry-go-round experiment. And this is because the merry-go-round, it was really hard to get it moving fast. And as soon as we stopped running around with it, it slowed down really, really quickly because there was a lot of friction. And we did explain this in our other answers. Thank you.
What effect did the changes you made have on the torque that exists on the heater product?
Torque is directly proportional to force exerted and distance. Since the force exerted by the group member on the seesaw was constant, we changed torque by moving the heavier person close to the pivot of the seesaw. The closer a group member was to the pivot, the less torque was exerted. That's because the moment of inertia would have made it smaller because. Okay, wait. Can someone explain this part to me? I'm sorry, can we cut for a second?
Where was the normal force coming from?
From holding the ball up with your hand. Come on, Ray, don't be a silly goose.
Is it when it? I'm pretty sure it's talking about when it's in midair. How is air resistance
No,
and normal force
no.
acting on it at the same time?
There's always air
No.
resistance. If you're holding, there's still air resistance on your ball in your hand.
Air resistance formula involves velocity. If velocity
Yeah.
is 0, air resistance is 0.
Where's velocity? You're spinning around.
Roll the
Are
rock.
you,
But
are you Ray?
And tangential to the circumference of the surfer, of the observer. Sorry, that's not right. Line tangential. Is that how you say it? We're gonna need to redo that. I'm sorry.
Hugh's face is the best.
Mass has no effect on the
Wait,
period
hold
of the
up.
swinging.
Don't we have to redo
What?
the first one?
Alexandra? Would you fly off the center? What, Alexandra?
Wait. Okay. So Shivam, you're gonna need to cut it after that question because
I'm gonna need to cut you after
the
that
next
question.
one. Hold up. The next one starts the.
go.
Trial 3. It's supposed to be 3. Faster, Srijith.
Spin. Alright, release.